Swayam Prabha. Digital India. Educated India.
Hello everyone. So, we are going to continue our fifth tutorial on Geology and Soil Mechanics course. Now, we were discussing about the problem of a consolidation, or the beginning of the starting of a consolidation, where basically we told that basically there was a lake that carved a deep valley, and we were asked to find out the pre-consolidation pressure, which I already discussed in the previous lecture, how to find out the pre-consolidation pressure, and now we have to find out the settlement of the clay layer beneath the lake. Now, this is how the present diagram looks like. The water table is here, and this side where basically the lake carved a deep valley has been given as 45 meter, while this height from here to here has been given as 1.5 meter, and this is the river, and this is the building. This is the clay layer of height 60 millimeter, 7.6 millimeter. So, that means 760 millimeter, 7.6 meter, 1000 millimeter, 760 00 millimeter. So, now we are asked to find out the settlement. Now, I said previously that if it is a general normally consolidated settlement, then we will use the general formula of CC, but if it is an over consolidated set, if the clay of layer is over consolidated, which it is supposed to be, because the lake, it was subjected to a greater pressure previously, now it has been subjected to a less pressure. So, obviously it is an over consolidated settlement. So, in that case basically we have to find out the value of CR or CS, whatever you call it, that is the reconsolidation index or recompression index, basically the recompression index similar to the compression index, and we have to evaluate the settlement. Now, as it has been discussed in the lecture that the recompression index is generally taken to be 1/4 or 1/10, whatever in between 1/10 and 1/4. So, here in this case we will consider it to be 1/10 for the case. So, 1/10 of CC or the 1/10 of the compression index for our case. So, first let us find out what is the settlement due to the normally consolidated clay layer. Now, delta S is equal to, we all know it is given by Cc by 1 plus E naught into H into log of sigma naught plus del sigma by sigma naught. Now, sigma naught has been already said to be the stress at middle of clay layer, which we found out to be equivalent to 160.5 kPa, and it has been said that delta sigma, that is extra stress imparted by building as equivalent to 0.9 dA, 0.9 decanewton. So, basically 0.9 dA Newton per centimeter square, and we have already said in the previous lecture as well that 1 dA Newton per centimeter square is equal to 100 kPa. So, this is equivalent to 90 kPa. So, from the formula now delta S is equal to Cc by 1 plus E naught into H into log of 160.5 plus 90 by 160.5. Now, H is the height of the clay layer, which we have already said to be 7.6 meter. If you want to find out in millimeter, that means it is 7600 millimeter. So Cc by 1 plus E naught 7.6, or maybe we will convert it into centimeters. So 100 centimeter into log of 160.5 plus 90 by 160.5. Now Cc can be found out from the general formula of Kempton's compression index, which basically says that Cc can be given in terms of liquid limit as 0.009 into WL minus 10, where WL is the liquid limit. Now it has already been given in the question that WL is equivalent to 45 for the clay layer, and the natural moisture content, that is W, is equivalent to 35% for the clay layer. This 35% was utilized in finding out the initial void ratio. So now Cc will be equivalent to 0.009 into 45 minus 10, which is equivalent to 0.009 into 35, which is equivalent to almost equivalent to 0.32. E naught we have previously found it out in the lecture, which basically is equivalent to 0.973. So this formula now comes out to be delta S is equal to 0.32 by 1 plus 0.973 into 760 log of 160.5 plus 90 by 160.5. So if you solve this, then it will come out to be eventually 24.4 centimeter, which is the normally consolidated settlement for the clay layer. Now if you consider an over consolidated settlement, that is delta SOC, this will be just 1/10 of this, because if you remember the formula, that is delta S is equal to Cs by 1 plus E naught into H into log of sigma naught dash by sigma dash. So now Cs is equal to Cc by 10. Now though this term may change, but it comes out to be almost like 1/10 of this formula, because this is the major factor that is governing the settlement. So in that case, delta OC will be equivalent to 2.44 centimeter, approximately equivalent. So in that case, the total settlement will be equivalent to delta SNC plus delta SOC, which is equivalent to 24.4 centimeter plus 2.44 centimeter, which comes out to be 26.84 centimeter. Now remember, this is all an approximate calculation, because neither the graphs are given here, nor you are supposed, nor basically the you know what is the pre-consolidation pressure. If you obviously know the pre-consolidation pressure, then obviously you have to find out the over consolidated settlement from the pre-consolidation pressure, because as you all know from the lecture that total settlement is given by delta SNC plus delta SOC, which is given by as Cs by 1 plus E naught into log of sigma P dash by sigma naught dash, where sigma P dash is the pre-consolidation pressure, sigma naught dash is the present vertical stress, which basically is less than the pre-consolidation pressure, plus Cc by 1 plus E naught into log of sigma P dash plus sigma naught dash plus delta sigma divided by sigma P dash into H. So here you have to know sigma P dash previously, either from the Casagrande's method, which we will discuss in the next problem. Delta sigma is known to you, and sigma naught dash is also known to you, because it is a present vertical stress, and H is the height of the layer. So in taking all these factors in account, you have to find out the total settlement considering both the normally consolidated and the over consolidated soil, depending on where your initial settlement, where your initial stress lies. So if your initial stress lies here and you are subject to a stress here, then basically you can easily see that it is a sum of over consolidated plus normally consolidated soil. But suppose let us say your initial stress lies at this point, then there is no over consolidated settlement, because you see that it has already covered the over consolidated settlement, if it has already covered the pre-consolidation pressure. So since it has already crossed the pre-consolidation pressure, that is sigma naught is actually greater than sigma P dash, so in that case only normally consolidated part would come into view. while basically if sigma naught dash is less than sigma p dash, then both the normally consolidated and over consolidated part would come in view. So, keeping all these factors in mind, now let us move to the next problem. Now, the next problem says that a highway embankment .40 meter high is to be constructed over a saturated homogeneous clay layer of thickness 2h equal to 4 meter. The clay is underlain by a sandy gravel which for all practical purposes is incompressible. Now, this term itself indicates, the term incompressible itself indicates that basically there is no settlement for the sandy gravel layer. The water table is at the ground surface. Now, let us construct this. So, this is suppose the ground surface, the water table is here. So, this is the clay layer. So, this layer has a thickness of, let us say how much is given as 2h equal to 4 meter. So, this is the homogeneous clay deposit. Now, this is the sandy gravel layer, and as it has been already said that this layer is practically incompressible. Now, the embankment is to be constructed at its top. So, this is the embankment, this is the high embankment, it is like a railroad, and this height of the embankment is given as 2.4 meter, and this height is given as 2.4 meter, and the length as it has been described in the figure is greater than 20 meters. So, this is of not importance, this is of not much importance, the length, because we are only interested in the depth of the embankment. And one more thing that is given here is the density of the embankment. So, the density of the embankment is given as 21 kilonewton per meter cube. This is given. So, now it is said that a sample of clay is recovered from a depth of 2 meter. So, the sample of clay is recovered from, let us say, a depth of 2 meters. So, basically this is the point from where basically the sample of clay is recovered. This height is given as 2 meter, and a consolidation test is performed so the results of the consolidation test are given here, like this is a consolidation test where this is the stress and this is the E. So, this is given in kPa or decanewton per centimeter square, and as we have already said in the beginning that 1 decanewton per centimeter square is 100 kPa. So, if I am going to use decanewton per centimeter square, just multiply into 100, you will get the value in kPa, and E has no units. So, 0.05 decanewton per centimeter square, 1.82 void ratio, 0.1, 1.81, 0.2, 1.80, 0.4, 1.74, 0.8, 1.40, 1.6, 0.80, and lastly 3.2, 0.16. Now, this is the consolidation that is given. There is also a compression given with respect to T in minutes in order to plot the coefficient of consolidation and E. So, for 0.1, now this is for 0.4 to 0.8 dA Newton centimeter square. That means, basically for this value and for this value, in between these two values, when basically the load was increased from 0.4 to 0.8, then how with respect to time the void ratio changed. This is how this table explains. So, for 0.1 it was 1.700, then for 0.2 it was 1.690, for 0.3 it was 1.683, for 0.5 it was 1.675, for 1 it was 1.650, for 2.5 it was 1.600, for 5 it was 1.550, for 10 it is given as 1.504, for 20 1.451, 50 1.432, 100 1.421, 200 1.418, 500 1.409, and lastly 1400 given as 1.400, and at 0 minutes obviously this is 1.740. So, see, the first and the last readings correspond to the void ratio as 0.4 and 0.8 respectively, and this is in between how the void ratio changed. So, the first question that is asked is the initial sample thickness is equivalent to 280, that means for the odometer sample or the consolidation ring sample it is equivalent to 24 millimeter, and the water content of the initial sample is 69%, GS or the density of the soil solids is considered to be 2.7. So, the first question that is asked is find out sigma C or sigma P, which is basically the pre-consolidation pressure. Then Cc and Cv. Now, we all know that Cc is the compression index, Cv is the coefficient of consolidation. So, that is what is the first question is asked. So, the first thing that you have to do is plot both the consolidation as well as the compression curves. Now, initially in order to plot the consolidation as well as the compression curves, you have to first find out that at 0 pressure what was the E naught or the initial void ratio. So, for this you have already been given W and GS 2.7. Now, we will consider for that, we will consider that in consolidation basically, since it is only the removal of water and nothing else, not air, it is only the removal of water. So, basically obviously the sample has to be saturated. So, the sample is fully saturated in the beginning, if the sample is fully saturated in the beginning, then S is equal to 100% or 1. So, from the initial relation, that is WGS is equal to SE, E naught is equal to W into GS, which basically is equal to 0.69 into 2.7 and comes out to be 1.86. So, this is the void ratio at a pressure of 0 kPa. Now, moving to the next void ratios, because it has already been given how the next void ratio varies. So, after 1.86 it becomes 1.82, 1.81, 1.80 and like that. So, the plot now looks like this, where this is in log scale and this is in linear scale. This is E or the initial void ratio and this is E or the void ratio and this is the sigma, which is dA Newton per centimeter square. Now, we have to find out the pre-consolidation pressure. Now, the best way to plot the pre-consolidation pressure is by Cassagrande method. So, I am not going to elaborate the Cassagrande method here, but there are other methods as well. The most useful method is the Cassagrande method, but there are some methods that gives a rough idea about how the pre-consolidation pressure is going to be. One of those methods is the double tangent method. In double tangent method, what you do is that you just draw a tangent from here, and just find out the intersection point, and you find out what is the pre-consolidation pressure. But remember that this pre-consolidation pressure may be overestimated or underestimated. So, that is why this method is not preferable. If you have time, obviously you must go for the Cassagrande method. So, if you follow Cassagrande construction, then sigma C dash comes out to be 0.5 dA Newton per centimeter square, and Cc we all know is delta E by log delta dash sigma dash. So, for sigma 1 dash is equal to 0.80 dA Newton per centimeter square, E1 is equal to 1.40, this one, and for sigma 2 dash is equal to 3.20 dA Newton per centimeter square, E2 is equal to 0.16. We will take any 2 points after 0.5 dA Newton per centimeter square, that means 0.5 means 0.8, 1.6, 3.2, any one of them you can take basically to find out the value of Cc. You can't take any value before 0.5, because before 0.5 it would resemble to the Ca or the decompression index, or basically you can also say the pre-consolidation part. Okay. That means in this part we can't take any value in this part, we have to take every value after 0.5 in order to find out Cc. We have to take every value greater than 0.5 dA Newton per centimeter square. So, that is what we took. We took two values after 0.5 dA Newton per centimeter square, one of them being 0.80 and the other one being 3.20, the last point and the first point. So, 1.40 and 0.16. So, delta E then comes out to be 0.16 minus 1.40, which basically is equivalent to minus 1.24, and log sigma 2 dash by sigma 1 dash comes out to be log of 3.2 by 0.8, which comes out to be log of 4. So, finally, we get the value of Cc as 1.24 by 0.602, because log of 4 is actually equivalent to 0.602. So, this comes out to be 2.06 or equivalent to 2.1. So, that is the Cc value. This is how you find out the Cc value. Now, you are also asked to find out the Cv or the coefficient of consolidation. Now, coefficient, in order to find out the coefficient of consolidation, you all know that there are a lot of methods available like T90, T50, but today actually we are going to discuss a different method from all of these methods. It is called T100 method. Now, a T100 method is kind of a different method from both the T90 and T50 methods. So, here also you first plot the graph, that means plot the compression graph. So, the compression graphs look somewhat like this. Now, in order to T100 we follow the T100 method because it is a very easy method than T90 and T50. In order to find out T90 and T50, you have to go through a lot of construction procedures, but in T100 actually it is pretty easy because it is similar to the double tangent method. like the one that I spoke previously during the construction of the pre-consolidation pressure. But like the previous one, this also is less accurate method, but today actually we are going to follow this method T100. So, T100 means you have to construct a double tangent from the linear part of this curve and the linear part of the compression curve. Now, this tangents, when they intersect at a specific point, this point is termed as a T100 point. You all know that this is the void ratio and this is the time, which is again in log scale. So, this T100 comes out to be 32 minutes. Now, once this T100 is found out, now find out the E100, that is the void ratio at the 100% consolidation. We can also use a different procedure by taking the 4 times of the length, that is T50 procedure, that we generally follow the log method, that also I am going to discuss. So, this is how it looks like. Now, first you have to find out the initial void ratio E naught. Now, you all know that the initial void ratio E naught is actually given as 1.86. Once the initial void ratio E naught is known, then you have to find out a time near origin. So, let us say we take a time like here, let us say we take a time like T1 equal to 0.1 minute. Origin means near the initial void ratio. You have to take another time that is exactly 4 times longer than the initial time. So, 4 times of T1 equal to 0.4 minutes, that is, let us say that is equivalent to T2. Now, for 0.1 minute we have the value of E as 1.7. So, T1 equal to 0.1 minute, we have E1 equal to 1.700, and for T2 equal to 0.4 minutes, we have E2 equal to 1.678. Now, remember this value is not given here. So, the best thing that you can do is find out interpolation between 0.3 and 0.5 and find out what is the value of E at 0.4. Okay, this is what it has been done here also, a linear interpolation between 0.3 and 0.5. I am not going to discuss the details here, but this is how you are going to find out the E2 value. That means basically you will find out a linear interpolation, simple linear interpolation between the 0.3 and 0.5. Once you know this part, so basically now you find out the value of E1 minus E2 equivalent to, because we know that delta E, because it is a linear portion. So, basically E1 minus E2 must be equal to EOC minus E1. So, from there we get EOC or the initial over consolidated part to be 1.721. Now, EOC, once it is 1.721, so we find out the E50 as EOC means the original, the initial part, and E100 means the final part, divided by 2. So, 1.721 plus 1.430 by 2, which is equivalent to 1.576. Now, I hope that okay, the E100 here is obviously at 32 minutes is 1.421, it is given here. Okay. So, no linear interpolation is required. So, E50 is 1.576. So, from there you can calculate the T50 as 3.7 minutes. Now, this is all possible because the scale of E is linear and the scale of T is in log. Okay, so, that is why you just linearly interpolate all the E's that you get and find out what is the value. Again, let me discuss this T100 procedure because it has not been covered in the lecture. So, in T100 procedure, what we do is that we just do a double tangent method from the linear part of the secondary compression, because you all know that this is the secondary compression. And this is the virgin consolidation curve. So, what we do is that we draw a linear we draw our linearly we draw a linear interpolation, or basically we draw a linear part of the virgin consolidation curve and the secondary compression curve and extend that so that they intersect at a certain point. That point is considered to be T100. So, T100 in this case comes out to be 32 minutes. If it is given what is the value of E100 corresponding to T100, that is good, otherwise you have to linearly interpolate to find out what is the value of E100. So, once you know E100, now you just take a point that is near to the origin T1 and you find out a point that is 4 times of that of the time to the origin, that is 0.4 here in this case we have taken. Now, for 0.1 the E1 was given, for 0.4 it is linearly interpolated between 0.3 and 0.5 to find out what was the value of E0. So, once the value of E1 and E2 was found out, now from the original relation we all know that since E is linear in that part, so delta E1 must be equal to delta E2, that is what we have found out in order to find out the EOC. EOC means the initial void ratio at the over considered part, that means at this part. So, E1 minus E2 equal to EOC minus E1. So, from there we found out EOC to be 1.721. Now, we know what is E here, that is at the start of the test. We know what is at 100% of consolidation, what is, because T100 corresponds to 100% of consolidation. So, we know what is the E100 here, this is the EOC and this is E100. So, once E50, once we know EOC and E100, E50 will be between them. So, it will be half of EOC plus E100 by 2, that is what we have done, and corresponding to E50 we have found out what is the value of T50. So, this is how you find out the time coefficient of consolidation CV or in a different procedure, or T50 in a different procedure, not considering T90 or T90 part, okay, or this is a T100 type of scale. Now, for T90 also you can find out T90. In that case what you have to do is that you have to find out, you have to first draw a line that is 1.15 times of the x part, and basically you have to see that where it intersects the curve, and then basically from there you can find out what is the value of the T90 part. So, now how to find out the coefficient of consolidation? The coefficient of consolidation can be found out because the height of the sample at start of consolidation under 0.8 dA Newton per centimeter square load is 2h. We consider this, that the height of the sample at 0.8 dA Newton per centimeter square load is 2h. Then we have 2h by 1 plus EOC, means EOC means the original. I have told you that in the beginning when basically we started the consolidation, this is, remember that this should not be confused with the, this should not be confused with this 0 and E0, because this 0 and E0 means it is the consolidation time, it is the void ratio at the time when basically there was zero pressure, but this is not corresponding to the point where basically there is zero pressure. It is basically at 0.4 dA Newton per centimeter square, and then the load has been increased to 0.8 dA Newton per centimeter square. So, that is why we get a EOC of 1.721. Remember this very carefully. Okay, this is quite different from the fact that this E0. Okay, do not confuse this E0 with the compression part, because compression, when it is in compression part, it is already been loaded. So, that is why you have to find out this EOC value, otherwise this value would have been given to you, or you have to find out from WG equal to ES. So, during that part when basically it was subjected to a load of 0.8 dA Newton per centimeter square, then its height was 2h. So, 2h by 1 plus EOC must be equivalent to 2h0 by 1 plus E0, because now we are reverting back to the original consolidation curve. That means we are reverting back to this original consolidation curve, the sigma e. So, from sigma e curve we can say that, because we know that delta h by h is equal to delta e by 1 plus E0. So, from this relation we can also say that 2h by 1 plus E0 c, that is h by 1 plus E0 must be equivalent to 2h0 by 1 plus e, because delta h by delta e is supposed to be same in both the cases. So, we get h is equal to h0 into 1 plus E c plus 1 plus E0. So, basically it was 12 into 2.721 by 2.860, or maybe I can write it in a more elaborate way, like 1 plus 0.721, because EOC is 1.721 and E0 we have already found out to be 1.86. So, 1.860. So that means H naught into 2.721, right, 2.860, and this 12 is basically the height of the sample. That also has been discussed here. See, 2 H naught is equal to 24 millimeter. So H naught is 12 millimeter because you consider the half of the sample. So in this case, it comes out to be 11.4 millimeter. So now CV is equal to 0.197 into H square by T50. So CV is equal to 0.197 into 1.14 square divided by 3.7 into 60, which comes out to be 1.15 into 10 to the power minus 3 centimeter square per second. Now this method, like T50 method, this method is also known as the log of time method. Like the square root of time method, okay, just like the part that is covered in the lecture, this is termed as the log of time method, because in this case you consider the log of time. Okay, so initially what you do is that you just intersect the, initially you find out the T100, and then basically from there you find out the T50, and once you find out the T50, then basically you find out the coefficient of consolidation from the T50. So in this case it finds out to be 1.15 into 10 to the minus 3 centimeter per second, and this formula is already discussed, that about how you find out the this coefficient called 0.197, because this 0.97 is found from the time factor TV for consolidation. Now after this part has been done, so the first question has been done, because the first question is said that you find out the pre-consolidation pressure, which you found out from the Casagrande construction, then CC, which is the compression index, that also found out from the Casagrande, that also find out after finding out the pre-consolidation pressure, then we found out what was the value of the CV. Now moving to the next question, which is said that total settlement of embankment. And after how long will this settlement be obtained? So this is the second question. Now in order to find out the total settlement of the embankment, now we have already found out that what is the value of CC, CV and all those factors. So now in this case we are going to find out that what is the total settlement of the embankment. So the first thing that you have to consider is that the thickness of clay layer. Now as you can see, the thickness of the clay layer is less, the thickness of the compressible clay layer is small compared to the width of the embankment, because the width of the embankment is considered to be 20 meter, while the thickness of the clay layer is just 4 meter. So thickness of clay layer is much less than width of embankment. So in this case it may be assumed that the stress distribution due to the embankment or due to the embankment on the clay layer is considered to be uniform, because if the width is like comparable with the thickness of the clay layer, then in that case basically the stress distribution may be non-uniform. But in this case, since the thickness of the clay layer is much less than the width of the embankment, so in this case the stress distribution is uniform. This is a very important thing. If the stress distribution is non-uniform, then we will see that how basically the stress distribution is non-uniform, in that case how the settlement is evaluated for the different stress distributions. In that case basically you have to either divide the sections or you have to adopt some other method in order to find the stresses at different levels. So basically in this case, since the stress distribution is uniform, so we can easily find out what is the value of delta sigma dash, because as I have said that only the depth of this embankment is required in order to find out the delta sigma dash, because you all know that the load at any point is whatever it is going to come out is gamma into z. So in this case the gamma into z comes out to be 2.4, which is the height of the embankment, into 21 kilonewton per meter cube. So, this comes out to be approximately 50 kPa. Now, since we are doing everything in dA Newton, so this is 0.50 dA Newton per centimeter square. So, once this has been done, then following, just like the previous day, we said that you have to find out the stress at the middle height of the clay layer. Now, here one thing I want to mention, that basically it may be also have been covered in your assignments, that if basically the clay layer has a very great depth, or basically let us say that the clay layer has a very extensive depth, in that cases basically in order to make the settlement calculation all more equivalent to the field conditions, what we do is that we just divide the clay layers into a number of subsections. So, suppose you divide it into 4 subsections. So, in that case what you find out is that you just form a table and you find out what is the, you just form a table and you find out what is the 1, 2, 3, 4, you just find out what is the stress at each of these sections. Let us say that for the 1, what is the stress in between, for the second layer what is the stress in between, for the third layer what is the stress in between, what is the fourth, for the fourth layer what is the stress in between. Then the stress increments in between for all these 4 layers, and you calculate the settlement for each of this layer individually. At the end you add up the settlements for all this layer to get the total settlement. This is a very important fact, you must remember this, that basically if the clay layer has a greater depth, in that case basically you have to divide the clay layer into a number of subsections, so that according to appropriate to you, it may be 2, it may be 4, whatever it is, but generally if it is like, but generally you should divide it into as many small sections as possible, so that basically the settlement becomes more close to the equivalent field conditions or the settlement that is observed in the field. So, in this case, since the settlement height is less, like 4 meter, so in this case we have to find out the stress at mid depth or at mid height of clay layer. Now, sigma naught dash is equal to H into gamma dash into clay. So, now you have to find out the gamma dash of clay. So, gamma dash is equal to gamma S minus gamma W by gamma S into gamma D, where gamma D is equal to gamma S by 1 plus E naught, or you can easily adapt away gamma dash of clay is equal to gamma B minus gamma W, that is gamma S minus gamma W, where gamma S is given by G plus E by 1 plus E minus gamma W into gamma W. G has already been given in the problem, which is equivalent to 2.7. So, 2.7, this is E naught by 1 plus E naught into gamma W minus gamma W. Now, E naught for the problem has also been given 1.86. So, 2.7 plus 1.86 divided by 2.86 into 10 minus 10, which comes out to be equivalent to half 0.594, because remember this is again in, I am doing everything calculations in dA Newton per centimeter cube. So, this is also in dA Newton per centimeter cube. Okay, so, this may not be 10. So, sigma naught dash, that is at mid height of the clay layer, it is obviously 4 by 2 into 5.94. So, this comes out to be 11.9 kPa. If this is in, if this is in 10, this comes out to be 5.94 kilonewton per meter square, meter cube, sorry. So, this is equivalent to 0.12 dA Newton per centimeter square. Now, if you do it in kPa, then this comes out to be 5.94 kilonewton per meter square, meter cube, sorry, and obviously multiplied with 4 by 2, because at the mid height you have to find out. So, it comes out to be 11.9 kPa. Now, you can proceed according to kPa, or I have, because all my units are in dA Newton per centimeter square, so we have converted this into dA Newton per centimeter square. So, now you have found out the value of sigma naught dash, and you also know what is the stress increment. So, just referring back, just like the previous problem we have said, referring back to the original definition of consolidation, delta S is equal to Cc by 1 plus E naught into H into log of sigma naught dash plus del sigma by sigma naught dash. So, what is the value of sigma naught dash plus del sigma dash? this is equivalent to, so what is this, what is the sigma naught dash? Sigma naught dash is 0.12, so 0.12 plus what is the del sigma dash? 0.50, so 0.50, adding both of them we get 0.62 dA Newton per centimeter square. So now, as I have said that in the first problem, that you have to check this part, that whether your present sigma naught dash is greater than the pre-consolidation pressure or less than the pre-consolidation pressure. Depending on that, here sigma naught dash plus delta sigma dash is equivalent to 0.62 dA Newton per centimeter square. And if you remember correctly, then sigma p dash or sigma c dash, whatever you call it, it is equivalent to 0.5 dA Newton per centimeter square. Okay. That is the pre-consolidation pressure. So obviously sigma naught dash plus del sigma dash is greater than sigma p dash or sigma c dash. Now let us refer back to the consolidation curve. So this is my consolidation curve. So this is my pre-consolidation pressure. Now you are lying somewhere here. So obviously the effect of pre-consolidation settlement is gone. That means only you have to find out the virgin settlement from the virgin consolidation curve. So if that is the case, then you can find out, since the compression curve is given to you, instead of using this formula you can directly apply the compression curve, that is delta H by H is equal to delta E by 1 plus E naught. So if that is the case, the delta H is equal to H into delta E by 1 plus E naught. Now you have to find out from 0.6 naught. Now let us find out the corresponding values. So sigma naught dash is equivalent to 0.12 dA Newton per centimeter square. Stress at the mid height of the clay layer. Corresponding E is equal to 1.80. Now how to find out the corresponding E? So from here you have to linearly interpolate. That is the only option. 0.2 it is given as 1.80. So either you have to linearly interpolate in order to get that value. And for sigma naught dash is equal to 0.62 dA Newton per centimeter square, that is a present stress condition. This is delta sigma dash plus sigma naught dash. We have E is equal to 1.56. Now this also you have to linearly interpolate between 1.7 and 1.40 in order to get the value of 1.56. So all these results I am neglecting here, but as I have said previously that you can just find out the linear interpolation. It is very easy to find out. Just find out the linear interpolation between sigma naught dash and delta sigma to find out the value of E. So E is equal to 1.56. Now just put the values. Now you see what is the change in delta E. So delta E has been changed from 1.80 to 1.56. So it comes out to be 1.80 minus 1.56, and your original E was obviously 1.80, and H is the height of the clay layer, which I have already said is 4 meter, so 400 centimeter into 1.80 minus 1.56 by 2.80, which is equivalent to 34.3 centimeter, or this is equivalent to 34 centimeter. So this is the settlement. Now you can also refer to this definition, delta S is equal to Cc by 1 plus E naught H into log sigma naught, whatever you prefer. You will see that the settlement is same in both the cases. Okay, it comes out to be 34 centimeter. This is an easier method because it just uses a linear method rather than using a log procedure. Okay, and it's more easier in that way. This is called MV method. Okay, either of them you can use. MV is, you know, which is coefficient of volume compressibility, and it is given by AV by 1 plus E naught, where AV is given by delta sigma delta E by delta sigma into 1 plus E naught. So that is what we have done here, the same thing, because delta sigma is the increment and we have considered the increment to be constant. So this is the best way in which basically you can find the settlement, and basically in order to find out this, if there was a pre-consolidation settlement previously, or basically if this was less, then in that case you have to refer back to this definition of settlement. That means basically you have to find out the pre-consolidation settlement first, then moving to the next part, the virgin consolidation settlement, and add up together to find out the total settlement. Now moving to the final question, which is said that determine the total thickness of the embankment and surcharge to attain the expected total settlement under the design embankment height after a period of 4 months. So, let us first see that 34 centimeter is the consolidation settlement that we have obtained. So, delta S equal to 34 centimeter. So, let us see what is the time taken to achieve this 34 centimeter settlement. Now, theoretically you can say, because you all know from the consolidation curve that the time taken is infinite, because this is the infinite long settlement, but general practice is that 100% settlement is obtained when U is equal to 99.4%. This is a very important part. So, basically if anybody asks you that basically what is the time taken for the settlement, it is not 100%, but actually U is equal to 99.4%. This is generally theoretically considered. Okay, but this is practically considered. Theoretically it is like infinite, but practically it is considered that when U or the degree of consolidation is actually 99.4%, then 100% settlement is obtained. So, now TV as we know is equivalent to CV by D square into T, where D is the drainage path, CV is the coefficient of consolidation, and T is the time taken for the consolidation. This is time taken, this is time factor, this is length of drainage path, and this is coefficient of consolidation. So, now T is equal to 2 into 200 square by 1.15 into 10 to the power minus 3. So, T, because this 200 comes from the fact that this is the drainage path. So, obviously it is D is equivalent to, I should have said this, that 4 by 2 which basically is 200 centimeter, the 2 meter. So, half of the drainage path, because there is a sandy gravel below which basically serves as a drainage, as well as the top there is a drainage. So, basically it is a half, it is the double drainage path. So, that is why double drainage means it is half the drainage path. If it has been a single drainage, that means below there was no drainage was permitted, then basically it had been a single drainage path, that means it had been 400 centimeter. So, T we can write as TV into D square by CV. Now, obviously TV is 2, because for 99.4%, if you find out what is the time factor, then it comes out to be 2. So, 2 into drainage path is 200 centimeters, so 200 square by CV, the coefficient of consolidation, which comes out to be, from our log of time method, it comes out to be 1.15 into 10 to the power minus 3 centimeter square per second. So, that is what I have written, and this comes out to be 805 days. So, this is equivalent to 2 years, 2 months and 15 days. This is the time that is taken to reach a settlement of 34 centimeter. But here it is said that how much total thickness of the embankment is to be considered, so that the settlement consolidates within 4 months. Now, it is obvious that if you have a settlement height of that height means settlement height of 2.4 meter, then obviously it is going to take 2 years, 2 months and 15 days to settle. So, in order to attain a settlement time, that means now the T has been given to you as 4 months or let us say 120 days. So, what should be the time factor? The time factor you can find out again from the given relation like CV by h square into T. So, now this is given as 120 days into CV, which is 1.15 into 10 to the power minus 3, and h, which is 200 square. Now, in order to convert this into seconds, so 8.64 into 10 to the power 4, this 120 days I have converted into seconds, so it is 8.64 into 10 to the power 4. So, 800 and so 0.298 or that is equivalent to 0.30. So, this is the time factor for the consolidation, and if you see the value of u, it comes out to be 0.613. So, for a settlement of 34 centimeter, it corresponds to 61.3% of total settlement. Now, we will stop here today and we will continue with this problem in the next lecture, and we will also discuss other aspects of consolidation in the next lecture. Thank you.